position, the exponent can be extremely influential over what the size of the base is, right?
Position as in like.
Meaning the functions, they're not just being products together, right? One is a power of the other.
Oh.
So its position within this expression could make it more influential, even if its rate of change is not superior to the other one.
I'm saying if the rate of change was the same.
The rate of change was, as I'm saying, if they're the same, it could be that since if it's the same, that this one, since its influence is different than what the base's influence is because of the structure of the function, it doesn't necessarily make them converge to a finite value.
I was just like, so you're saying f of x would be dependent on what g of x would be. Is that what you're trying to say?
Well, let's say you take the same two functions. If you have e to the x raised to the e to the x power, so now both f and g are the same function, right?
Yeah.
Or let's write it different. I'll write it different. Let's write it like this. E to the x raised to the e to the x. They certainly have the exact same derivative everywhere, even, no matter what you're heading towards, right?
Yeah.
So now it's the 0 to 0 case, right? It's the 0 to the raised to the 0 power case.
Okay. So wouldn't it just be 0, 0 then?
Would it be 0 to 0? I mean 0 to the 0 power? No, it's never going to be. E to the x is never going to reach 0 for either the base or the power.
Because you said that e is not going to be 0.
Right. It's heading towards that, though. This is this case. It's a crazy one of these cases, but it is this case. And the derivatives, from what you described, Roger, the derivatives are exactly the same everywhere. E to the x and e to the x are the exact same derivatives, the same function.
Like they're gonna reach there at the same time, right? That's what I'm trying to say.
Yes, they're both heading towards 0 at the exact same pace. That's correct.
So
but it could be, because this one is the power and this one is the base, the fact that the power might have more influence over the base, or the base, depending on what function it is, they want the same function exactly, might have more influence over the power in certain cases.
Okay, so one might negate the other one from getting there is closer.
Yeah.
Okay.
Even if the rates were the same. Yeah.
Okay.
It's not just like a simple product or something, right?
Yeah, like
where they're influencing each other in the exact same. A product, the two functions influence each other in the same way, times, right?
Yeah.
But this is, I'm a base and I'm an exponent. In a product, it's, I'm a, what do you call it?
Just a term.
No, what do you call it? I'm a factor and I'm a factor, right? They both influence each other in the exact same way.
The whole point. So we're taking powers and differences and products, we're changing them to quotients.
We are doing that. We're changing the quotients so we can apply a certain rule. That's true. Yeah.
Like, why do we exactly do that? Like, what is the mechanic behind it? What is the reasoning that we can't take derivatives? I know it has something.
Are you saying like it should be the same as the derivative of this raised the derivative of that?
Yes. Like it's. What I'm trying to understand is like, what exactly are you trying to? What do you exactly accomplish by converting those into a quotient difference? I mean, the intermediate.
Into a quotient?
Yeah.
Because then you can apply the L'Hopital's rule. The L'Hopital's rule only applies taking the derivative of the two functions, and that being the exact same as the original limit of that quotient is the limit of its quotient. I cannot say this.
Well, it follows a rule. That's the reason you can apply. You have to.
That's right. I cannot say this. This is false. X goes to whatever equals, you know, lim of f prime raised to g prime as x goes to whatever. I can't say that. The L'Hopital's rule only extends to quotients. That I can just take straight derivatives of two functions and reapply the limit. Only applies when they're in the form of a quotient.
Because the rate of change for both of them are. So when you have these two functions, what are you trying to find? The horizontal asymptote, or like a point where both of them meet?
I just want to know what they're doing. No, it's not a point where they meet. That's for sure.
It's like, well, just where they're
in
heading.
Some cases, it's a horizontal asymptote.
So
in some cases.
Just
where every case.
Just where they're heading to. That's all you're looking for.
I just want to know where this thing's headed towards. This crazy little thing. Where's it headed towards?
The quotient and that quotient just shows you exactly where it's heading towards, just because it has some. It already has something built in it where it's showing you where it's going.
In a sense, yeah. Yeah, there's something more particular about a quotient that allows this to happen, as opposed to other operations. You have to ask the L'Hopital why specifically a quotient. last one, infinity raised to 0. That's your last case. Okay? So there are 3 cases to indeterminate powers. These are 3 cases.
I thought you were done with like that whole part. I was like,
Nope, we need to do an example of at least one of these so you guys get a feel for how to deal with the powers. The basic rule is apply a logarithm, like you did before for logarithm differentiation, right? How do you get the power down there so you can deal with it? You apply a logarithm. So it's not much different from that. Let's see. That was logarithm differentiation, right? We're now trying to apply this to limits. So we'll take x to the 2x. Limit of x raised to 2x power. This is number 39. X is heading towards 0 from the right. Why is it 0 from the right? Why not from the left? Or why not just 0? Because you don't allow negatives for the base, right? When you have tower functions, the base can never go negative. So that's why most people go 0 from the right. So now, which case is it? 1 to infinity, 0 to 0, or infinity to 0? Which indeterminate power do you have?
Maybe 0 to 0?
What are you guys talking about?
0 to 0?
0 to 0, man.
because x is
What's x heading
0.
towards? X is the base, 2x is the power. What's x heading towards? The base is heading towards 0, the power is heading, that's what the notation is mean. What is the base heading towards? Sorry, I guess I didn't explain properly. What is the power heading towards? So it's a 0 raised to 0 case, right?
That was pretty cool.
Really?
I don't know, it's just after
I
all
think
that
you had
other
too
math.
much Boyo Comparo then.
After all that other math, it's just like, I just lost track.
You just, yeah, I hear you. I hear you. It's like a freight train before and now.
Yeah.
So much.
I thought it was in slow motion for a second. All right.
Slow motion, I felt like he went like super fast forward.
All right. So now you know it is an indeterminate power. You need to change it to an indeterminate quotient. So the technique you're going to use is a logarithm. So what you're going to do first is apply a logarithm to your expression, ln of x to the 2x, right? You have superimposed the logarithm onto the function that you're trying to take the limit of. Oh, I hate prepositions. Right? So that allows you to take down the 2x to the outside as a coefficient function, 2x times ln x. It should now appear as an indeterminate product. This is the normal thing that happens. Don't worry, we're not going in circles yet, right? It always becomes an indeterminate product. Okay? So now it's what? What case is it?
0 times infinity?
Correct. This now is 0 times infinity case. Negative infinity, but it doesn't matter, right? Right? Because this heads towards 0.
And you're still plugging in x for 0, right?
Correct.
Okay.
And a logarithm, as you head towards 0, heads towards negative infinity. Okay? So it's 0 times negative infinity case. This is what should always happen. You should have an indeterminate product. So now what you want to do is change it to an indeterminate quotient. So here's where you have to make a decision. Do you want to write this as? Here are your 2 basic options. Since there's no obvious way to change it into a quotient. So you can write ln of x over 1 over 2x, or you can write it as 2x over 1 over ln x. This is a very basic technique that you're going to use quite frequently to do these problems. Okay? You have to make a decision. Which one do you want? Okay, top one it is.